Welcome back, everyone. I have the honor to share the second session of today, which is about key exchange and key encapsulation mechanisms. And Edoardo will start off this session with a talk on a note on non-interactive key exchange from Code Equivalence, which is joint work with its nodes, Antti Maridoa and Paolo Santini.
Thanks, Andre. Thank you for helping me not chair myself. Would have been interesting, but I was not meant. So the story is I was not meant to give this talk. It was supposed to be my co-author Lindsay. She couldn't give the talk. So To and Paolo are both giving other talks later. So in the end, it's like, okay, I'm going to give the talk. This is it's a small note on a work about code equivalence. So I thought it's interesting anyway to share this with the audience because we haven't seen anything about it yet so far, not in a detailed fashion anyway, right? So we'll quickly give the motivation for this work and talk a little bit about code equivalence problem and its applications to cryptography, and then we'll describe this attack that as again it's a very small note on the security of this proposed idea. Okay, so the motivation is a slide that I usually can completely skip in this context, which is about post-quantum cryptography, and we are all scared about Shor's algorithm, etc., etc. So we do post-quantum crypto, yes. So we can easily skip this part. So this is the maybe the more interesting part. So traditionally, as we have seen already, all of yesterday, I just realized all of yesterday was like entirely McAleese. The entire day. So this is in fact the traditional approach. So what, when anyone thinks about code-based cryptography, this is McAleese, right? So the traditional approach is to use error correcting codes. And so in general, although we have seen binary error correcting codes, this works in general for any QRA code. This is also why I was talking to Andre. I was like, I've seen look about FQ. So in general, code in theory can take any finite field, doesn't have to be binary, and you just consider a code to be a subspace of the vector space of dimension n, of length n and dimension k, of course. And so we can define this code via usually a generator matrix as a basis. Just choose some vectors to be your basis, and then you can also use a parity check matrix, which is essentially the kernel space. Okay, so this is two completely equivalent ways of defining the code, and the magical property is that we have some decoding algorithm that is able to correct up to a certain number of errors. Okay, so the idea of McAleese, and in general, how do we use coding theory for cryptography? Again, in the traditional way of looking at it is that we rely on the hardness of the coding. Okay, so we have this decoding algorithm that gives us the possibility to correct errors, but it's in fact hard to decode a random linear code. So if I just take a matrix of the correct size, this gives me a code, right? But in fact, most often than not, this would be just a completely random code with no structure, right? So what are the odds? I just pick a matrix and it's a copper code, right? This is basically. So in general, it's hard to decode codes when I don't know anything about some underlying properties. And we can formalize it in several ways. My favorite one, I think the favorite one by everyone, is the syndrome decoding problem, which means that if I take a matrix H, right? So this is kind of like a parity check matrix candidate sort of thing, and a vector in the space Y, and I fix a target weight. Then it's the goal is to find a word of low weight, and this is really the crucial point, such that the product H times Z is equal to Y. This is the syndrome. This is called the syndrome of E, and this is what is called the syndrome decoding problem. And this is the computational version. We are actually looking to find this, right? So now we have basically almost all the ingredients for a trapdoor, which again, I suppose this was McAleese's original reasoning, right? So I have a code I know how to decode, and then in general, it's hard to decode this code. So I will try to disguise my private code into a public code to make it look random. So it's important that the chosen code is actually unrecognizable once you transform it via some transformation, and you scramble it. And McAleese's original idea was extremely exemplary in this way. It was doing exactly what we know is now the code equivalence problem. Okay, so let's look at this. This is a notion that is basically standard in coding theory, like it's one of the staple things. So we say the two linear codes C and C prime are permutational equivalent if, well, surprise, if there is a permutation between the two codes that connects them. Okay, so we map the code words of one code into the other one by applying a permutation, which means you just permute the coordinates, right? You can imagine we are permuting the columns of our matrix. Okay, we can also extend this notion to linear isometry, so we can take it up a notch if we consider coefficients. Now we live on a finite field that is not binary, and so it makes sense to imagine that we can define an equivalence that is not just about permuting, but also we have some scaling factors here. So we define a linear isometry via a vector v of non-zero elements, right? And then we're not only permuting the coordinates, but also scaling them in a fixed way. And then we talk about linear isometry. And this is the extension of the basic idea of permutation equivalence. There is also a notion, more advanced, for example, for semi-linear isometries, where we consider field automorphisms in the case that we have any. But this is actually not relevant, for example, to our work in cryptography. So we usually tend to not go too deep into this. Okay, so code equivalence is the idea of, like I take my code words and I map them into code words by permuting and scaling. So we can describe it efficiently, for example, using the generator matrices, right, or parity check matrices. But with the generator matrices, the idea is that two codes are permutational equivalent if there is a pair of matrices S and P. S is the invertible matrix, my change of basis, and P is the permutation such that G prime is equal to SGP. So if G is the generator matrix of the first code, and then G prime is the generator matrix of the second code, I can find this pair of matrices that connects them. Yes. And then this is interesting because so you see, like, it's not just about the permutation, but in fact, you have to take into account the fact that you may have some change of basis in there. And equivalently, you can use what's called monomial matrices to represent linear equivalence. So monomial matrix is like a permutation. It has like exactly one non-zero element per row and column, but it's in fact non-zero. So it's not necessarily one. It will have exactly that coefficient. So you can imagine that it's like a permutation times the diagonal matrix where you have these coefficients. Okay, so once we represent the code equivalence in this way, it's easy to see that in fact it can be seen as a group action of simplifying somehow this group here on the set of full rank matrices, right? So again, I can imagine my set of full rank matrices is giving me the generator matrices for the codes, and I have this action here. And this is a key point because we've seen group actions kind of come up everywhere, especially in cryptography. We'll talk about this in a minute. So once we have this notion of code equivalence, it's natural to ask, okay, if I take two codes, are they equivalent or not? Right? This is the most intuitive question. And in fact, this defines what is known as the code equivalence problem. And traditionally, we have, for example, the flavor of code equivalence, that is permutation equivalence. It's asking about, are they permutational equivalent or are these codes linearly equivalent, right? And these are actually two flavors of the same problem. And it turns out that the security of the hardness of this problem is like related, but it really strongly depends actually on what kind of version you are considering, right? So if you're talking just about permutation, you're asking whether that there exists a pair S and P that maps these two matrices, or the pair S and Q. Okay, so a couple of quick words about hardness. This is not the main focus on this talk. Talking about the hardness in general is entirely another matter. But the problem was studied for a long time, and the conclusion with this paper by Petranka and Roth is that it's very unlikely that the problem is NP-complete. And this is a major difference compared, for example, to syndrome decoding, right? Which we know is NP-complete. We love it. It's a great thing. But here, unless the polynomial hierarchy collapses, this is not going to be an NP-complete problem. So does it mean that this is useless? No, right? In fact, we have a relation. You can see it's very closely related to the graph isomorphism problem. And this is actually, on one hand, it's like, oh, not very good because graph isomorphism is not really hard. On the other hand, it doesn't really tell us anything. It doesn't mean that this is bad. Yeah, it's just kind of like we have this relation. It can be exploited in certain situations, but it's also not very helpful in general. And so we do have, in fact, some existing algorithms that efficiently attack particular cases. And this is important. We have some algorithms by Sandrier and by some other people that exploit certain particular properties that depend on the code and how it's chosen. In particular, for example, they look at the size of the hull, which is the intersection of the code with its dual. So if the code is kind of like unlucky or chosen in a specific way, then there are very efficient solvers for it. But this doesn't mean that the problem is easy in general. In fact, what I mean is that unless you, so if you choose the code not in the unlucky way, but according to certain criteria, then it's actually easy to find intractable instances. And once you are able to like discard all these efficient attacks, which is easy enough, then essentially the best attack is, well, I don't know if underlying exponential complexity is vague enough, but what I mean is that the best thing you can do is try to map the two codes by looking at their code words. Because in fact, the idea of equivalence is that the code words are mapped from one to the other code. And for example, things like the Hamming weight are preserved. Right? So what you can do is look for code words in the two codes and then see if you can map these, because the Hamming weight has to be the same. And so while looking for code words is ISD essentially, right? So in the end, if you discard the easy instances, the best thing is basically doing ISD a bunch of times and then trying to map your code words. Okay, with the usual improvements that you can imagine, et cetera, but the essential idea is that like it kind of boils down to a code word search anyway. And so, as we have seen by Andres' excellent talk, this is kind of an exponential sort of algorithm. Okay, so what about cryptography? And the question here that I posed myself some time ago was like, could we actually use this as a standalone problem? Right? Because for years, everyone thought about, yeah, this is coding theory, cryptography, we do the trapdoor, hardness of the coding, etc. Yeah, this is great. But actually, you know, as we have seen, Macalise has some great things and some not so great things. And it's kind of like, this is just one way of doing things. But the reason why I was asking myself this is that, you know, it's a group action, like we said before. So we actually may be able to do this, some different things, right? So in fact, the situation for linear isometries really recalls the same one as other group actions. And the queen of group actions in this case is obviously the discrete logarithm situation that we have here. We're acting on the group, right? And this is great. So in fact, discrete logarithm is sort of like overkill. It's like a beautiful example of group action, but it's extremely powerful. But the thing that kind of prompted a little bit the reasoning was more the fact that we now have another group action, right, on isogenies. And this was like extremely popular. Everyone loves isogenies. It's so cool. And you know, like actually, what is an isogeny? Is like mapping one curve into another curve. Right? It's this map. So it's kind of the same thing. You just map a code into another code with this linear isometry, right? So it's like a broader idea of sort of isomorphism between these two objects. You just have to define your realm, and then so you know we're basically attempting to do the same thing. And in fact, several constructions can be adapted using code equivalence as your building block, right? For example, and this is not, of course, it's not the focus of our attack talk, but it's just to give an example of what can be done, right? Product placement. we can have a zero knowledge protocol. It's very easy to construct a zero knowledge protocol that is based exclusively on the hardness of code equivalence. We did this in 2020, and we called it LESS. Linear equivalence signature scheme, because the idea is, of course, once you have a zero knowledge protocol, you can use Fiat-Shamir, and this becomes a signature scheme. And actually, we have a signature scheme, and traditionally, people in code-based cryptography like kind of agree that the signature schemes in code-based cryptography are generally bad. So this was kind of something that we were struggling to do before. And now we have a signature scheme, and it actually uses completely different tools from what we use traditionally, right? And then we can obviously optimize this. We can work on this. So we did some tweaks that, again, are only possible because we're using a specific zero-knowledge protocol. And so we can do things like we use a fixed width string of challenges, and then we can use multiple keys and play with the soundness in this way. And so we actually can have access to a variety of optimizations to not just the basic scheme that we normally don't have. So here is like a one-slide recap of the LESS identification scheme, which is like the core, and then can be evolved into some very cool modern schemes. So the idea is that we use purely the group action. We take we have a public code G. We generate the public key by setting an equivalent code, right? And then the prover does his commitment by fixing like an ephemeral instance, right? So this is another linear equivalent code defined by Q tilde. Here you see that I use the systematic form because there is this kind of particular thing that you need this invertible matrix here distributive basic metrics on the left to define the problem properly. And if you don't have any metrics on the left, then it's actually easy. If you take just G and G times Q, it's actually easy to recognize the transformation. Right? It's trivial because you just see the permutation of the columns, even with the scaling factors. But if you do have that, then you have a variety of options for this, but you can always reconcile because the systematic form is defined for each code in the end, right? You just do your Gaussian elimination. So you can kind of play around this. And then you commit to this, right, with your hash function, and then the verifier is going to ask you either to reveal your ephemeral instance or the actual instance where you use your private key. Yeah, so it's one of the two, which means you have sometimes have 1/2, right? And of course you reply with either the Q tilde or the private key Q inverse Q tilde, and then it's verified accordingly. You set either the public hold or the public key. This is like the standard kind of like group action 1/2 zero knowledge protocol, and we can do it entirely with code equivalence. Okay, and we get something really interesting in the end. Okay, but here when you think discrete logarithm, you told me discrete logarithm, my ears are buzzing, right? Because actually discrete logarithm is very famous. I want to say arguably for two things. Right? One thing is that we can do signatures like DSA and ECDSA and this kind of stuff, and this is actually not what we're doing here, unfortunately. But there would be an even better signature scheme if we could do that. And the other thing is, of course, the Diffie-Hellman. This is what this logarithm is known for. So what about the Diffie-Hellman, in fact? And here, yeah, so I have to take a step back and have to say, like I said before, discrete logarithm is very special. In a sense, we were lucky. We found out, like discrete logarithm and it has beautiful properties. And in fact, they are kind of like extra properties. Not all group actions have this. For example, the code equivalence group action is not transitive in the sense that it's not true that if I take any two codes, they necessarily are related by some isometry. This is not true. So the space is not full, right? And there are some other properties that are also missing. So then you have to see in the specific protocol what are the properties needed, because for the zero knowledge protocol, you don't need this. But for some other things, for example, like I said, if you try to do DSA or like Schnorr type signatures, it doesn't work. And if you try to do the Diffie-Hellman, the main problem is that it doesn't commute, right? So the product of two permutations is not commutative. Okay, so this is kind of unfortunate. And then there were several ideas that were explored by myself as well as other people, and we kind of discarded a bunch of ideas like how can we kind of go around, like for example with SIDH they do some clever mechanism for which they are able to like, yeah, it also doesn't commute, but then the diagram can somehow commute. Yes, I'm not going to go into detail in that. So we kind of explored a bunch of ideas and we discarded essentially all of them. And then recently we saw this preprint by Zhang and Zhang, and they tried to solve the issue in a very intuitive way, which for the record was like one of the ones that we had sort of analyzed before and discarded, and they were like, oh, really? Okay, so let's have a look at this. And the idea was to split the action into two parts. And this could be a way to go around the problem, right? So if you, for example, imagine that your permutation / monomial anyway is just affecting like half of the columns in some way, and then the other one is only affecting the other half, then of course they don't intersect, they are disjoint, so then they commute. Yes. So here's the idea, the very simple idea. We take Alice and Bob, they want to do the Diffie-Hellman. So one chooses a permutation on the like odd column acting permutations, and the other one chooses the even column one, for example. Right? It could be, I don't know, first half, second half, you define whatever, but for simplicity, it's just like two disjoint sets. And then they do the thing that we expect them to do. So they, they choose the S. Again, this is necessary for security, right? They publish their equivalent codes. They exchange these, and then they obtain the key with some reconciliation function, which in this case, for example, is computing the systematic form, right? And then, of course, once you have the share secret, you take the hash, whatever, you have your share secret. Okay, so the idea is very simple. It's exactly what you would do with the group action. And of course, the protocol works because in this case, the two monomial or permutation or whatever, they do commute because they are disjoint. Okay. All right, so this looks very good. In fact, too good to be true. And so, to be honest, the authors start. So the paper is actually kind of like semi-rigorous, if you want. But the idea is they propose a new computational problem that is ad hoc, that is defined like the code equivalence problem. But the request is to find a Q in this union, right? So the Q is either affecting the odd or the even columns. Anyway. Right, so the question is, given G and G prime, do we have a map of this form? And the reason, in fact, it's possible to write down our reductions. The authors do this to the linear code equivalence problem. And the issue here is the trap of the security reductions, right? Is that the authors kind of overlooked that, yes, if you build the code in a specific way, then there is this reduction. But it doesn't really tell me anything about the average case. And it's not really meaningful. So the fact that some certain worst case instance can be reduced to code equivalence, it's not an argument for this problem being actually hard. Because this is one thing that we face, like how is it that our attack works, but there is a reduction, right? So the problem is that there is this gap. So you have to be careful when you do that. And in fact, we have an attack that works with overwhelming probability and is the one that you can imagine. So, if you choose one of the two parties, it doesn't matter which one, say Alice, and you remove the columns that are affected by your permutation, then the other columns don't move. And so you can actually generate a new instance where, say, consider only the even columns, well, actually there is no permutation here, right? And so then, basically, if the code rate is 1/2, then all of these are square matrices, and you can just resolve the system of equation and find the S. Okay, and once you find the S, you're basically done, because as we've seen before, like if you don't have the S in front, then you're just asking to find the permutation between G and G times Q, and it's just like mapping the columns, right? So the problem is actually trivial. So if the code rate is 1/2, then the attack is straightforward, because all you can do is just solve the system of equations. If n is greater than 2k, so then the system is overdetermined, and the attack obviously works because in general, like the system is overdetermined, so maybe it doesn't actually have a solution, but in this case, a solution exists, so you can immediately find it, right? And so the only instance in which possibly we have a hope of making this work is whether the system is underdetermined, right? So if the code is rate different from 1/2, and then in this case, we have a number of free variables that come out of the system, and you could actually make this very large, right? So the number of free variables is given by this. And the authors were kind of aware of this, and they say, okay, we can make this very large and we can avoid the attack. And the crucial observation is that, of course, if two codes are equivalent, so are their duals, right? So the fact is that, and this is now staple for me, like whenever I think about code equivalence, I always think at like what is the best between the code and its dual, and this is the one you want to attack, essentially, right? So if you do that, then essentially that you can just use parity check matrices, and they use the same Q. Right? The invertible matrix may be a different one, but it doesn't matter. The map is the same map between the two codes. Yes, and then so you can basically attack the duals instead of the normal ones, and you can just apply the same attack as before in the overdetermined case. So there is no escape in this. Yes, and so we were actually quite, if you want, explicit. We said, we take the parameter sets that they proposed. These are kind of like standard sort of sizes, even bigger than what we actually use, for example, for the signature scheme. It's like relatively small codes with large Q. Yeah, so in fact, for a signature scheme, we use larger Q and even shorter codes. But anyway, this is kind of like standard thing. They propose these parameter sets. You see that this is kind of like 6 less than half. It's like this is enough already to have like a large free variable space, and we even added like an extreme one, which is we follow the same criteria, right? We just choose like a really big parameter set, and in all cases, we just wrote down. So this is my student, wrote down a simple Magma script, and the scheme is broken immediately. So I mean, there's clearly like a fundamental flaw in the approach, and the authors acknowledge this, and we drew the paper. And so it means that this simple solution just cannot work. You have to come up with something a lot more clever. And again, the personal journey is that we tried several ideas trying to come up with some way to reconcile these codes, but it's not so easy. In fact, I think it would be extremely interesting to design a Diffie-Hellman-like scheme using code equivalence. Generally speaking, after I don't know if I'm already quite late, the idea with code equivalence schemes is that the mathematics is easy, the operations are easy, and the objects are a little bit bigger depending on the sizes that you get. So it's kind of the opposite of what happens in isogenes, where you have these like extremely small objects, but they are horribly slow. So we have like some sort of like a dual, it's like a group structure, and you just have to like play around with the properties and see if they fit your scheme. And the more things you're able to design, it provides like an interesting approach to code-based cryptography that we didn't have before. So this is the end of my talk. Thank you for your attention. I will take questions if you want.
So we have maybe time for one or two quick questions.
Key sizes, and do they get better when we use this assumption?
Yeah. So you're right. So the key sizes are actually quite small because the codes that you use are very short. As you see, like Macaulay's codes are like thousands of length, and here we use codes that are 200 long, and with a large finite field, which anyway is like a logarithm in the key size. So it makes a big difference because the code is obviously a quadratic sort of object, as you imagine. So like if you shrink the code quite a lot, then you get something in the order of 4 or 5 kilobytes, 10 kilobytes, depending on the particular instance that you select. And in fact, in the signature scheme, we have some options for trade-off as well. So we can maybe choose a longer signature, shorter key, or vice versa. We can look at the sum of the two. We have some flexibility there, but overall, we get something in the order of 10 to 20 kilobytes for the whole package, or depending on the, yeah.
So yeah, I was wondering, so with group actions, the issue is that they are pretty inefficient, right? So when we look at technologies, for example, we can
Yep.
around more or less this vision more or less. So have you looked at the more like concrete properties of codes that may improve this information theoretic time of one bit? Those group action evaluation?
So the question is difficult. Yeah, it's difficult to look at properties of codes that specifically you can exploit. So you have some things, for example, you have things like the weight enumerator, that is like one of the invariants that traditionally people consider for code equivalence, but this is both too broad because it doesn't cut quite close to the specific map that you're using, but like if you're just using codecs that are equivalent to each other, then they all have the same weights, and so it's very broad, and it's also like extremely expensive to calculate. And so yes, one thing that it would be interesting to find is some invariants and some properties that allow for some cuts and for some efficiency. Again, like I was saying, like what they do with SIDH, and then they use the kernels and they use some tricks and stuff. So yeah, it's very, it would be interesting to see something like this.
Maybe one last question.
Yes, we looked at it. There is even a paper that kind of discusses this direction to hidden subgroup problem, but in the end, in particular, my co-author Jean-François Bias is like a big quantum person, and we concluded that it's not really the main threat. It's not really meaningful, like what they are able to do. In practice, what is the most concrete threat is the usual threat. Is what I was saying before. Basically, what you do is like a search for code words, and you can do this quantumly, and you can quantify this. So basically, the attacks on code equivalence, you can do the same treatment. You can groverize the search part, and this provides a certain speed up. But in the end, it's like quantumized things. In fact, we are now looking at quantifying this precisely because, like I was hinting at Andre, like we have ISD very well understood in the barrier case, not so well understood in the QRE case, and even less understood in the quantum QRE case. So it's kind of nice to, so now with Paolo Santini and the other co-authors, we are looking at making a precise estimate. But I think, yeah, the hidden subgroup problem thing is not the main threat in this case.
So let's thank the speaker again.
Thank you.